So this next notebook, we're staying with the lag model, but we're considering instrumental variables estimation, which requires the selection of the right instruments. Other than that, it's the same as the standard two-stage least squares, which we saw a few weeks ago. I call it spatial two-stage least squares. The only spatial thing to it is that we pick the spatial lags of the exogenous variables as instruments for the spatially lag dependent variable. That's the only special spatial part, so to speak. So these are the same modules as before, except instead of ML lag, we're going to import GM lag. The variables are a little bit more complicated than the previous case in maximum likelihood. So we have the same initial setup, but we are allowing the economic hardship index to become endogenous. Just as an example, you could probably argue that some of these other ones should be endogenous as well, but it's just an illustration of the mechanics, not of the substance, right? And then again, just to keep it simple, as in previous exercises, I picked the X and Y coordinates as instruments. Are these not necessarily the best or the only ones? Probably not, but it's good enough for our illustration here. And then we take two weights. First set of weights are queen contiguity weights. Those we get to construct a spatially lag dependent variable and the spatially lagged exogenous variables as the instruments. We need regular weights for that. The second set of weights, the K10 TRI, are triangular kernel weights, which we'll use to get hack standard errors. So the two big differences between a maximum likelihood and instrumental variables estimation of the spatial lag model is that here we can have additional endogenous variables, which we can't with maximum likelihood. And here we can have robust variance estimates. So we can have standard errors based on white, standard errors based on hack, which allows us in kind of a cheap way to have a spatial lag model corrected for possible additional spatial correlation in the error terms. To the extent that the hack standard errors correct for that, we're good to go. Because the main effect of the autocorrelation in the error term is on precision. We can either run the fancy model, which we'll talk about at the very end, or we forget about it and we just go with hack standard errors and we say that's good enough. It corrects for the loss of information that we have because of the autocorrelation. So that's all done in this cell. And then we just set up all the variables. This is a little bit more complicated than before. If you recall, we have this problem reading kernel weights. So we have to kind of force them to have the right class. Otherwise, it generates an error. We have our Y and X. We make a distinction between endogenous variables and exogenous variables among the X's. And we need the instruments. To make our life easy, we load all these things up ahead of time. And I can't remember whether I ran it or not, so now I ran it. We did this before, I'm not going to repeat it. We ran the OLS. We saw evidence of strong evidence of lag, some evidence of potential spatial Durbin. When then we ran the SLX, we didn't see that strong an evidence anymore, but we ran spatial Durbin anyway. So as I explored in the lectures and explained in the lectures, the way we go about this, finding the instruments, it's all based on the reduced form, this expression here, where we pick up the suggested instruments from the power expansion of this inverse here, which gives us the spatial lags of the x for different orders. So Wx, second spatial lag of x, and so on. Then to run this is very simple, probably too simple. You do gm lag, specify y, x, the weights, and then here I turned off the spatial impacts. We won't dwell on that. It's the same logic as we saw for maximum likelihood. So we get the results. Interestingly, we see that our estimate, spatial autoregressive coefficient, is in the same ballpark as the one we get for maximum likelihood. Remember, we got 0.39151. This is 0.37, basically 0.38, and the other one was 0.39. So that's pretty close. We have the standard errors. Everything is significant. This, just like in the previous case, becomes non-significant. The magnitudes are very similar to the maximum likelihood. This is not always the case by any means. In fact, if they're very different, you want to start thinking about it, especially in smaller data sets. The choice of the instruments affects the precision a lot. Okay. If you look at the top listing here, there's no likelihood. No likelihood, no AIC, no SC, none of that. But you still have the pseudo R-square, squared correlation, and the spatial pseudo R-square. These numbers are very similar to what we had in the maximum likelihood case. It was all around 0.64, 0.65. So basically, we get the same type of result. What you get is the standard, see, it says spatial two-stage least squares, has the exact same structure as standard two-stage least squares. So it has the instrumented variable, which is the spatially lag dependent variable, and then the instruments, which are the spatial lags of the exogenous variables. So this is exactly as if I had time, and you can actually do this for yourself, run a two-stage least squares regression that doesn't know that it's a spatial regression. So you create a spatially lag dependent variable using lag spatial. You create a spatially lagged exogenous variables using lag spatial. Then you run a standard two-stage least squares where endogenous is your spatially lag dependent variable. Instruments are your spatially lagged exogenous variables, and it will be exactly the same result. The test for remaining autocorrelation doesn't find anything. No evidence here. Okay. You can use higher order lags. You set this by means of the W lags option argument. So let's say we wanted to get second order spatial lags. We get basically the same result, a little bit different in the standard errors. But you see, this becomes very monstrous here. And if you remember with the SLX, we start to get real problems with multicollinearity once we start bringing in too many higher order lags. If you recall in the last exercise when we ran SLX model with SLX lags equal 2, we had VIFs that were off the charts, right? So individual spatial lags were almost perfectly predicted by the other spatial lags with R-squares of more than 0.99. That's not a good thing. So everything else is the same, predicted values, residuals is the same as before. All that stuff, you can look at the notebook for maximum likelihood, it's exactly the same thing. What is not the same and is new are the robust standard errors. But again, there's nothing new here. This is exactly what we've done with two-stage least squares before. It's the exact same argument. The robust equal white. We saw that in the class last week. That gets us this monstrosity in terms of the expression for the variance matrix, all these matrix multiplications. But at the end of the day, it's pretty straightforward to do. And it gets us a set of estimates of the spatial lag model that are robust to heteroscedasticity of unknown form. So this is something that we cannot do with maximum likelihood. And as we know, heteroscedasticity is predominant in cross-sectional data sets. So I would highly recommend that you run at least the white one. The hack one, in this case, doesn't necessarily make a lot of sense because we have no evidence that there is any remaining autocorrelation. If we had evidence, if this would be significant, then it would make sense to put in a hack standard error. So this is something I also want you to pay attention to in terms of your project. Don't do stuff you don't need to do, right? Here I do it because I want to show you everything you can do, but it doesn't make any sense. There is no point correcting for spatial correlation when there is no spatial correlation, right? So don't do it. Heteroscedasticity, yes, but spatial correlation, only if needed. You're not going to run a spatial lag model if there's no evidence of spatial correlation. Why bother, right? So this is the same thing. They're here to show you it's exactly the same as we did before in the standard OLS and the standard two-stage least squares. We said robust to hack, and we have to specify kernel weights. And then we get a new set of standard errors. In this case, it doesn't really matter anymore. So once you do hack, this is a little wordy, but it tells you what you need to know. Again, since you're already correcting for spatial correlation, there is no point testing for spatial autocorrelation. Otherwise, you'd be questioning your own thing, right? So my logic or my practical advice is check out this test. By all means, correct for heteroscedasticity. If there is no remaining autocorrelation, don't bother with the hack. There's no point. But if there is, then either you estimate a model with both lag and error, which I don't recommend either, but we'll talk about that in a couple of weeks, or you do the hack correction, which in my opinion is the better way to proceed. You just kind of correct for it and be done with it. Spatial multipliers, impacts. I'm going to go very, actually, I'm not going to go at all. I'm just going to show you very quickly that it just, like before, it gets you the same thing with the impacts, direct, indirect, total, same thing. We talked about this. This we haven't talked about is how do you put in additional endogenous variables? So the only thing that changes is that just as in the two-stage least squares case, we have to add these two arguments. The list of, I mean, at this point, it's actually a data frame, of the endogenous variables, and the instruments. These do not include the spatial lag. So the spatial lag part is taken care of by the fact that you're not running two-stage least squares as such, but you're running GM lag. GM lag takes care of the spatially lag dependent variable being endogenous and requiring the spatial lags of the exogenous variables as instruments. That's done. This part is not done. You have to say, in addition, I'm making the economic hardship index endogenous, and I'm setting X and Y as the instruments for that. Then everything else is the same as before. The other additional option is whether you compute spatial lags of the other instruments or not. And I can't really give you any advice on this. Sometimes it matters, sometimes it doesn't. I'm not aware of any kind of extensive simulation experiments. It's hard to do because unless you have a system of simultaneous equations, it's not really unambiguous to pick the instruments. So if you wanted to set up a simulation, you would have to know what are the exact instruments that you need to pick. And then you could tell whether it makes a difference to also spatially lag them or not. There is no a priori theoretical reason to do this because they're not part of the reduced form. They're out of it, right? So it's just all the same stuff, except that now we have the economic hardship index included as instrumented, and here are all the instruments. The coordinates, the spatial lags of the coordinates. Actually, for coordinates, it doesn't make a lot of sense to take the spatial lags. Coordinates are spatially correlated by construction. They show your position in space. So your position relative to your neighbor, because it is a neighbor, their x coordinates and their y coordinates will be very close to your x and y coordinates. So the spatial lags of coordinates don't actually make a lot of sense. So this would have been a case where you would set lag q equal false, right? It doesn't really give you much, but it gives you everything else. The test for remaining error autocorrelation. So then again, you can do robust standard errors, you can do hack standard errors, and all that good stuff. And then finally, spatial Durbin model. Again, it's all the same. We have GM lag, Y, X, W, and then the only way the spatial Durbin is distinguished from the standard spatial lag is by sticking in SLX lags larger than 0. The default is SLX lags 0, which means no WXs. Now, pay careful attention to the output. It all looks the same, except for here. This is all taken care of under the hood because WX is already in there as a variable in the model. You cannot use WX as an additional instrument. Remember, all the X's are already instruments, but now all the X's include the WX's. So then if you say the W of the WX's, what are these? Okay, so you have, think of it as X and WX, right? W times X is WX, but you already have WX. So that's a waste. W times WX is twice WX. So the only new instruments that you add beyond what you already have in your regression are these second order spatial lags. So that's the difference between a standard spatial lag and a spatial Durbin. And the spatial Durbin, because WX is already in there, you cannot use it as an additional instrument. It already is an instrument by virtue of it being one of the explanatory variables. So that's why we have to use the second order ones. We have the common factor test. We have the AK test, the direct and indirect effects. All this is the same. This is the only difference with spatial Durbin, right? And then, it's same interpretation. And I believe there's one more spatial Durbin with endogenous variables. And again, same thing. We have these two need to be included. We have to set SLX equal to 1. And then we have the output. And now we have X and Y as instruments for our economic hardship, which is endogenous, all these second order spatial lags, and then the first order spatial lags of X and Y, because why? I set lag Q here to true. If I want to change it, I'm going to just set it to false and run it. Then you see they're not spatially lagged. Now, what we have here is, let me see if this is the case. Okay. Yeah. What's that mean? You can't have a row coefficient larger than 1. It's not allowed. It's outside the parameter space. But if you paid careful attention, when I change this to false, we no longer have the problem. We still have a problem. Don't ever come to me with autoregressive coefficients that are this large. That's way too large to make any sense. Think about it. What is an autoregressive pattern? It's a pattern where everything is the same, closer things more so. But if everything is the same with a distance decay of 0.98, it basically doesn't decay at all. So then everything is the same everywhere, which is not useful information. So this model doesn't make any sense. That's what I'm saying. So don't come to me with models that don't make any sense. Just because you can run it doesn't mean you should. Right. And that's both the power and the danger of something like spreg. You can run everything. Does it make sense? To me, no. You can enforce a warning message where it just will not even give you the estimates. But honestly, I would have to look it up. It's something like hard bound equal true or bound hard equal true. I can't remember, but you can set this as an option in here, and then it just will not give you an estimate. Because it is larger than 1, it will say, no, it's no good. Okay, let me run it again. So when you have this, this is the bad one. since it's larger than 1, you can't do the inverse. The power approximation doesn't hold anymore, so we can't get the impacts. Right. If you said, I believe it's hard bound, if you said hard bound equal true, then it will not even give you the estimates. It will say, this doesn't make sense.